In this video, we're going to talk about radian measure. So previously, in any time where you were dealing with an angle of rotation, you would have dealt in degrees, where a full rotation was 360 degrees. But in more complicated maths, and as time goes on, things start getting measured in radians instead. So we've got to first of all establish what is a radian. So the diagram on the right shows an arc which you have of AB, which is a length r, and that r is equal in length to the radius of the circle. So in other words, we've got a circle here with a radius of r, and we've got an arc marked out on it on the edge of a sector which has the same length as the radius. When you get to a situation like that, the angle in the center of this sector is equal in measure to 1 radian. Now if the length of the arc AB was 2r, then the angle would be 2 radians, and so on up for that. Alright, so we're just going to take a look at a few different ways that this is going to impact and how this is going to work out for us. So let's take a look at the first bit. Since the circumference of a circle is 2 pi r, in other words, 2 pi multiplied by the radius, then there are 2 pi radians in one complete revolution. So that means that 2 pi radians is equal to 360, or pi radians is equal to 180 degrees. That's a very important one to make sure that we remember, because it's going to be useful for converting to or from radians. Now there's a whole bunch of frequently used angles that are given in degrees and radians, and you can see them in the box here. 0 degrees is obviously 0 radians. 30 degrees is pi over 6 radians. 45 degrees is pi over 4 radians. 60 degrees is pi over 3 radians. 90 degrees is pi over 2 radians. 180 degrees is pi radians, as we said above. 270 degrees is 3 pi over 2 radians. And 360 degrees is 2 pi radians. Since pi radians is 180 degrees, that means that 1 radian is equal to 180 degrees divided by pi. And that would give us 57.3 degrees. Now for converting to or from radians, there's a fairly straightforward calculation method for doing these. So we'll start off with 2 radians. Okay, so since 180 degrees is equal to pi radians, which we've established above, that means that 1 degree is equal to pi over 180 radians. So if we're converting some angle theta degrees to radians, what we're going to do is we're going to multiply the number we have, this theta angle, by pi over 180. So converting 2 radians is as simple as multiplying by pi over 180 and then simplifying whatever fraction we get from that. Now converting from radians is relatively straightforward. If we're given radians in the form of pi over 6 or 3 pi over 2, if pi is involved in this, then all we're going to do is we're going to sub in 180 for pi in our radian amount, and then work out the fraction from there, or work it out from there. And we'll see examples of that below in just a moment. So let's take a look at a couple of examples of converting to and from radians. So we've got a bunch of measurements in degrees and a bunch of measurements in radians, and we're going to convert to radians and then from radians. So 2 radians to start with. Converting 2 radians, we have to multiply by pi over 180. So for this one here, it's going to be 30 times pi over 180. And if we simplify that out, 30 over 180 is just equal to 1/6. So we end up with 1 times pi over 6. In other words, we just get pi over 6 for this one. So it's pi over 6 radians. For our next one, for 45 degrees, it's going to be the exact same process again. It's going to be 45 multiplied by pi over 180. Well, 45 over 180 is a quarter, so we just end up with pi over 4 radians for this. And we're going to go to the same process for the next one. It's going to be 60 times pi over 180. Well, 60 over 180 is a third, so we end up with pi over 3 radians. And the next one, same thing again. It's going to be 90 times pi over 180. 90 over 180 is a half, so we just end up with pi over 2 radians. And for the last one, it's going to be 120 times pi over 180. 120 over 180 is 2/3, so for this one, we get 2 pi over 3 radians, like that. So that's a selection of angles converted from degrees to radians. And let's look at a bunch of angles given in radians, and we're going to convert them back to degrees. For each one of these, we're just going to sub in 180 in place of pi, and then work out the sum we've got. It's nice and easy for the first one. Pi radians is just equal to 180 degrees. That was nice and straightforward. For the next one, it's going to be 180 over 6, which is going to be equal to 30 degrees. Next one's going to be 180 over 4, and that's going to be equal to 45 degrees. So the next one we've got 2 pi over 3, so it's going to be 2 multiplied by 180 all over 3, and that's going to give us 120 degrees. And for our last one, it's going to be 3 times 180 all over 5, and that's going to give us 108 degrees, like that. So that's converting to radians and from radians. And there's a couple of other little formulas that we need to remember for this. Let's take a look at them here. So our arc length L, which we can see on our diagram there, the arc length L, is equal to the radius times the measure of the angle in the middle, as long as that measure is in radians. That's how that works out for this one. So our angle measure theta in radians multiplied by the radius will give us the arc length. And the area of the sector, which is marked in green in the diagram here on the right, is 1/2 r squared theta, where theta is in radians. So let's just see an application of that to start with. So for the first questions here on the left, we've got to find the length of the arc of a circle of radius 4 if the angle subtended at the center is. So in other words, if the measure of the angle at the center is, first of all, 2 radians, and then 2.5 radians. Well, that's straightforward enough. We already know that L is equal to r theta. The length of the arc L is what we're looking for. So for part 1, it's going to be L is equal to, and it's a radius of 4, and a measure of the angle in the middle of 2 radians, so times 2. So it's just going to be equal to 8 centimeters, like that. And for our next one, since we know again that L is equal to the radius times theta, where theta is in radians, our L this time is going to be equal to 4 times 2.5, which is just going to give us 10 centimeters. So that's finding the arc length when we're given the angle in the middle and the length of the radius. Let's take a look at different use of these, as well as finding the area of the sector. So for this one, the radius of a circle is 5 centimeters. We've got to find the area of the sector if the length of the arc is 6 centimeters. Okay, so the length of the arc is 6 centimeters. We've got to find out the angle in the middle for this, because our angle here, our formula here requires theta, and we haven't been given theta yet. But we do know that L is equal to r theta, and we've been given the length of the arc, it's 6, and we've been given the radius, which is 5. So 6 is equal to 5 theta, which means that in this case, theta is equal to 6/5, like that. So that's the angle in the middle, it's 6/5 radians. That's our angle in the middle there. And now we can just fill in all that information into the formula for the area, where area is equal to 1/2 r squared theta. So it's going to be 1/2 times the radius squared, where the radius is 5, so it's going to be 5 squared, multiplied by theta in radians, which is 6/5. And if we multiply that all out, we'll get 15 centimeters squared for our area. So that is a brief look at how radians work.